Hello. Today we'll be discussing the contents of week 7 and some questions pertaining to that. In the previous weeks, we have looked at different muscles, their mechanics, their force, movement relationships, etc. In this particular week, we'll mm, look at different tissue types and what kind of and one of the major uh, biological material, which is bone, and the dynamics associated with bone. So coming to the first part, which is tissues and what types of tissues are there in human body. uh, this particular section is called as tissue biomechanics, wherein you study the physical properties and the mechanical behavior of biological materials. And given that this is a biological material, it's not the same as a industrial material such as steel or wood or uh, copper or a copper rod, etc., which in which the properties at every given section is equal. So if you were to consider a rod of steel versus if you were to consider a bulk of tissue, the properties in steel, if it's uniformly formed, is if you take a cross section here versus if you take a cross section here, the properties are going to be same. By properties, we mean the mechanical properties, the composition, all of this is going to be the same. Whereas in case of a tissue, uh, it's not the case. Now these if you are looking at a section within the human body, these units can either have a unilayered tissue, wherein you have, say, one layer of, say, epithelial tissue, or such as the skin, where if you are just considering the surface of the skin, it's one layer of epithelial tissue basically. So even within that, depending on, if you have wounds, the properties will be different in the wounds versus a normal patch of skin. But if you are considering it in 3D, it's not a single layer. There are multiple layers of tissues, and each layer has its own function and therefore its own biomechanical properties. So, most of the biological materials are therefore non-linear in their material properties, such as the mechanics of it, which basically is the stress-strain relations or the stress and rate relations. And we'll see what these are in the subsequent slides. And in the geometric response, which is the strain displacement relations. And these, there are in general, there are differences in the homogeneity of the biological materials. Say if you are taking a you are looking at something here versus if you are looking at something here, the material properties are going to be different. And this particular portion is called inhomogeneity. Another term that we often observe in biological materials is anisotropy. So isotropy essentially means uniformity in all directions. In all directions. So essentially anisotropy is the opposite. So it's, if you have a tissue which is uniform in, say, this direction, if you were to say take a reading in this direction, the readings are going to change, the modeling is going to change. So therefore biological materials in general are more difficult to model as compared to steel, aluminum, glass, boards, etc. The same goes for fluids within the body. There are different kind of fluids. There is blood, there is lymphatic fluid, and all of these, the properties of these biofluids are also very different. Their flow is different. So therefore the shear that they put on the tissues that they encounter is also going to be different. Okay. Now coming to the types of tissue, there are epithelial tissues, which is essentially everywhere in the body, and the main function it lines the organs and it secretes different hormones. Usually these epithelial tissues are very closely packed, or they are, another term that is there is, they are jammed. The organization is such that they are jammed. uh, the they they have intercellular material, but that intercellular material is very little. They are under some nervous control, but the nervous control, if this is a layer of epithelia with different cells, the nervous control would lies here or here. It's very rare that the neurons interject into the layer like this, and there is no blood supply. Whatever blood vessels lie would lie in either on the top side or the bottom side of the epithelial layer, and therefore, but you find this everywhere: skin, intestinal lining, all of these are epithelial tissues. Next is nervous tissue, which is essential for body control, which relays the information that is generated in the brain. These consist of neurons that transmit electrical signals and neuroglia that support the neurons. These are accessory cells of sort. The glial cells are accessory cells of sort, which help in maintaining the neuronal health. And they do this by insulating them or by anchoring them to blood vessels. Next is the connective tissue, which includes bone, cartilage, dense connective tissues such as ligament and tendons, and loose connective tissue such as fat, blood, and lymph. By connective, it should connect something, right? So even blood and lymph are considered as connective tissues, essentially because they can help in communication between two very far apart portions within the body. And same goes for, similar to uh, actually different from what we saw in epithelial tissues, connective tissues have nerves in them. They are supplied with nerves, and there are scattered cells in the background. And usually for connective tissues there is something called as the matrix. This matrix usually consists of fibers and other ground substances, and essentially these fibers, or in other terms, this matrix can be termed as extracellular matrix. It's usually outside of the cells. It uh, forms the ground layer. If you were to imagine the cells as bricks, the matrix forms the mortar that keeps everything together. And these are usually collagen fibers that are very tough and flexible. They have a very high tensile strength, or they can be elastic fibers made out of a protein called elastin. Collagen fibers are made out of collagens, and these collagens are of different types depending on where the collagen is located. uh, Elastic fibers are made out of elastin, and there are other reticular web-like fibers present, which are composed of different proteins. The ground substance includes cell adhesion proteins. Whatever the components of the extracellular matrix are, it provides a source of adhesion uh, for the cells. So the cells will have uh, some like receptor. It's like a ligand receptor interaction. The cells might have some molecules which will bind to the matrix, and therefore this particular interaction that occurs results in adhesion of the cells to the matrix. Another um, another type of tissue that is present is the muscle tissue, that controls the movement, and it includes both passive as well as active components. The passive components include the contents of the muscle tissue, such as the connective tissue, and the active components include different motors that are that are usually under neuronal control. uh, there are multiple types of tissues, as we saw. So these tissues can be differentiated in terms of hard and soft tissue, depending on what kind of material they are. Now, hard tissue includes bone, cartilage, teeth, nails. Soft tissue includes fluids, usually blood, lymph, or excretions, uh, muscles, tendons, ligaments, and organ structure, which can have different kind of cells. um, Even within these are the types of tissue we'll be looking at. There are other types of tissues, such as uh, endothelial tissue, which lines the blood vessels. Mesothelial, which forms the sac, which protects the stomach, intestine, keeps the stomach, intestine, everything in one place. There are different types of tissues. Although these are the tissues that we'll be looking at in particular. Okay, so hard tissue is bones, cartilage, teeth, and nails. Soft tissue is different kind of fluids, muscles, tendons, ligaments, and organ structure. And within this, when we are looking to model different material properties, uh, bones are one of the most important hard tissues, and muscles are the most important soft tissues. And whatever modeling we do, biomechanical modeling we do, in terms of movement dynamics, etc., usually uh, restrict to these two kinds of tissues. Okay. Now, as we know, there are in a human body there are 206 bones. Out of these, 26 are in the spine or the vertebral column, and there there are different shapes and sizes of the bones. Some of these bones are very large, such as the femur, radius, ulna, humerus, etc. Some of these bones are very small. There are bones within the ear, known as incus, malleus, stapes, which are responsible for the proper hearing. And there are also very small bones, although not as small as ear bones. There are bones within the palm or within the leg, which are very small. There are very large bones, such as the pelvic bone, and so therefore there is a very wide range of uh, sizes and shapes in within a single human body. So these bones can be long beam-like, such as in arms, legs, and extremities. They can be annular structures, which is what we find in the vertebral column, where there is a hole in the middle for the spine to pass through, uh, spinal cord to pass through. There are other areas where there are annular structures, which essentially lets blood vessels, and neural supply to pass through. And there are also flat plates and shells, such as scapula and the skull bones, which are here. These skull bones are there are if you feel around in the skull, there are these small cracks, or if you see an x-ray of a skull, there are these small cracks which are fused now, but when we were kids, there were it wasn't very tightly adhered to each other. The skull bones were not very tightly adhered to each other. These don't have any movement as such, but it's very important for protecting the brain. And there there are very thick packing that occurs between two skull bones, and therefore they don't move around in adult humans. Again, the bones are not dead, they're living tissues. they have a vascular supply, they are capable of growth, repair, regrowth, they have neuronal supply to some extent. So they are living tissue for all intents and purposes, and therefore it's a dynamic system, although the time scales are not the same as the muscles, but they are a dynamic system. Okay, now coming to the microstructure, uh, which can be, every bone will have a similar microstructure, but it is easier to visualize within a large bone such as femur, which is, for all of the modeling purposes, cylindrical, is a cylindrical shell. It has a very hard outer surface and a very soft inner core. This, the hard outer surface is known as compact bone or cortical bone, um, and the soft spongy interior is called as trabecular or cancellous bone. Uh, in so a lot of strength in the bone comes from the cortical portion. The spongy bone has its own points, and it is also a site for uh, creation of various, for generation of various blood cells. uh, this portion is also called the marrow, and uh, in case of immunodeficiencies or in case of immunocompromised individuals, uh, in case of cases where the blood cells are not properly forming, a bone marrow transplant is something that is an option, and this essentially results in the host, the person who is receiving it, the recipient, to have, it enables the recipient to form their own blood cells instead of regular transfusions. um okay, sorry. Yes. So there is a outer compact bone, a hard bone, and an inner spongy bone. Both of them have their own functions. um so the if you are looking at just the outside, the the hardness that is there is usually due to deposition of various mineral salts. These are essentially based on calcium and phosphorus, and are known as hydroxy apatite crystals, or hydroxyapatite compounds. So essentially, if the patient has weak bones, they are usually prescribed to have calcium, and these calcium tablets usually have phosphorus in it, uh, or vitamin D3 if there is a problem with the absorption of calcium. Okay. Now these hydroxyapatite salts or hydroxyapatite crystals are held together by a matrix of collagen, which is what we looked at here as tough and flexible fibers that usually are present within connective tissues. These hydroxy, basically the compact bone is a sum of salts, collagen, and some other cell types that we'll see in the subsequent slides. So now coming to the cell types that are there are, so it's not that all of the cell types are isolated to the spongy area. There are cells within the compact bone as well. The compact bone is a living tissue. It's not, it has its own blood supply. It's not only the inside of the bone that has a blood supply. So the bone tissue is comprised of four different types of cells: osteoblasts, which are basically responsible for forming the bone matrix. These are secretory cells, therefore. osteoclasts, which are responsible for reabsorption of cells, absorption of bone. They are responsible for breakdown. Osteocytes, which maintain the bone tissue. Basically, osteocytes are generated from osteoblasts, and they they are essentially covered with the various secretions that a osteoblast secretes into the matrix, uh, and it helps in maintenance of the bone tissue. The other cell type that is there is osteogenic or stem cell or osteoprogenitor cells. So essentially, if you see osteo, it relates to the bone. These osteoprogenitor cells are responsible for making osteoblasts, which can again differentiate into osteocytes and perform different functions. And therefore, each of these cells have a unique function, and together they maintain the homeostasis of the bone tissue via bone remodeling, replacement of the old bone tissue with the new bone tissue. Homeostasis is basically maintenance of the normal in simple terms. It's not a disease state, it's the maintenance of a normal state within a tissue. These cells, like other tissue cells, are again nourished by a blood supply. Another system that is another portion of the another structure that is usually found within long bones are known as Haversian systems. These Haversian systems are usually present within long bones, in the cortical or the hard compact bone. They are essentially a system of canals, like canal-like structures. These essentially are the Haversian systems, and these Haversian systems are where the blood vessels, nerve fibers pass through the bone, and they can communicate through the osteocytes, and the osteocytes themselves are connected to each other via canaliculi, which are projections, which you can see here. These are the canaliculi. And the basic unit, so when we saw muscles, we saw that sarcomere is the basic unit. In here, osteon is the basic unit, which is a sum of Haversian canal, osteocytes, and the canaliculi that the osteocytes project out. Okay. Now coming to the physical properties of the bone, such as the density, and as we saw before, as with any biological material, they are not homogeneous, and they are also anisotropic. So the properties, if this were a bone, the properties here will vary from the properties here, and if you are looking at a cross section here, the properties here won't be the same as the properties here, might not be the same as the properties here. So you, whatever descriptions, whatever values are put forth, or whatever description is associated with density or strength or elastic moduli, is usually usually in approximate values. It is usually found by taking multiple readings along different bones and then averaging it out, but that average does not say anything about the distribution itself. So all of the values that we'll be seeing are approximate values. The mass density of the cortical bone is approximately 1800 to 1900 kg per meter cube. However, the density of trabecular bones, which is the spongy part, varies considerably depending upon its porosity, from 5% to 70%. So if the trabecular bone is very packed, the porosity is low and the density is high. Whereas if the trabecular bone is has a high porosity, it has low density. And again, depending on what kind of tensions the trabecular bone is under, the porosity is also defined by that. What kind of nutrition the individual has, the porosity is also controlled by that. It's controlled by a variety of factors. Okay. uh, Next, coming to the physical properties. So whatever uh, just to reiterate, whatever properties that we'll be seeing are general average values. They are not exact values, or they do not talk anything about the distribution that might be there in a system. uh, in general, for bones, it's stronger in compression than in tension, and it is weakest in shear. So the forces that it can tolerate under compression is more than the forces that it can tolerate under tension, and the weakest force that it can tolerate is in shear. So if this were a bone, compression is when a force like this is applied, and it essentially tries to decrease the size of the bone. It might not be successful, but it tries to decrease the size of the bone. Tension is, suppose, when uh, the the forces are applied in this direction, wherein the the intent is to elongate the bone. Shear occurs when there is forces applied on the sides, in this side, on this side, and the bone is very weak to shear forces. Giving some values, the cortical bone has an approximate compressive strength of 190 megapascals, or 190 into 10 to the power 6 pascals, which is a very high force. So this is essentially the highest compressive force that the compressive force per area that the cortical bone can tolerate. Highest tension is 130 megapascals, and highest shear is 70 megapascals approximately. Uh, the elastic modulus, which we'll be looking at in the subsequent slides, it essentially is the inherent property of the material as to how stiff the material is. Higher the elastic modulus, uh, the more is the stiffness of the material. So higher Y, more stiffness. The elastic modulus of the cortical bone is approximately 20 gigapascals. Uh, Again, for trabecular bone, the differences are not very well known. The strength and modulus depend upon the density, which depends, as we saw here, on the porosity. However, there is a model which is tried to model the dependence of the strength and a modulus on the density of the bone, and the model is that if this is the density, then the compressive strength is in terms of square of the density, whereas the elastic modulus is in terms of cube of the density. That's how the dependence is. Okay, now when we look at a bone, they're not essentially cylinders. They have a weird shape. So why do the bones have such shapes? One reason might be that uh, they need to have connections with the bones that are above and below them, so here and here, to enable locomotion and other kinetic functions. They also need to have a very high load bearing capacity, because they in the lower limb, the bones have to tolerate the weight of the upper body of the individual. So they are designed as beams with high axial strength. They need to be able to control the forces, tolerate the forces in this direction. And the condyles, which are essentially here, are, are in an ideal shape for load bearing surfaces. Okay. Now coming to Wolff's law of bone remodeling, um which incorporates three concepts that were established in early 19th century. Uh, the first one is the bone is deposited and reabsorbed to achieve optimum balance between the strength and weight. So if there is higher strength, higher weight that the bone has to tolerate, it will have to deposit more material on the cortical bone. The trabeculae in the cancellous bone tend to line up with the direction of principal stresses that they experience. And both phenomena occur through self-regulating mechanisms that respond to mechanical forces acting upon bone tissues. This remodeling is not a very fast process. It might happen in the time scale of a few days or few weeks or few months, depending on how extreme the conditions are. But this is a continuous process that happens. So if the applied load is more, external forces change in shape, and the strain leads to sensory perception, which leads to cell activation. Either they can activate osteoclasts to reabsorb the bone, or osteoblasts to uh, uh, deposit more material on the compact bone, which leads to remodeling or reabsorption of the material. Woolstar basically, Bull stated that trabecular bone tended to be formed during growth and development in orientation that correspond to principal mechanical stresses. So if the stresses are in this direction, the trabecular bone is organized such that the trabeculae is in this direction. Okay. From any mechanical perspective, the biological components can either have passive or active forces. When we look at muscles, it's a sum of active force and the passive force, whereas passive force is the resting state and active force is when there is an intent for movement. uh, Passive components such as bone tendons respond to outside forces in ways that are either independent or dependent on time, and they are also remodeled depending on that. Active elements such as muscle generate the forces, which are usually controlled by motor proteins. So whenever there is a whenever muscles are getting modeled, there is a need for incorporating both active elements and the passive components, because the muscles themselves have both of these terms. Okay, now coming to Hookean or linear behavior, which is the simplest type of passive response, in which the materials behaves like a harmonic oscillator spring. So, and if there is any deformation in this or in this direction, they are linear with the applied forces and the stresses in whichever direction the force is, and this response is independent of time. However, this is an ideal situation. It's no material is perfectly harmonic, and most material deviate from this Hookean behavior. Coming to non-Hookean behavior, which is essentially deviations from the Hookean behavior, wherein the deformation is depends non-linearly on the force or the stress. However, if this deformation is still reversible, it's elastic. If this deformation is non-reversible, it is called plastic. Okay. plastic deformation, which is not which is essentially irreversible. Um, Essentially, the material returns to its initial state when the stress is removed, both in linear and non-linear parts of this elastic regime. And beyond this elastic regime is the plastic regime. Uh, and beyond the plastic, there is fracture or failure of the material. Okay. Now coming to perfect springs, which are Hookean, essentially they obey Hooke's law. Now Hooke's law is F is equal to minus Kx, where F is the force, uh, K is the spring constant, and X is the distance by which the spring is extended. In any scenario, there is a equilibrium of resting length of the spring, which is basically the passive portion, where there is no restoring force. So F is essentially 0. So if the new X is the deviation from this equilibrium length, the force is minus K delta X, wherein delta X is X minus X naught, which is the change in the length. Now coming to elastic properties of the of any system, any object that is modeled as a spring has a cross-sectional area of A and the length of L. We can, so the initial Hooke's law was if you divide F by A is equal to minus K, ignore the negative sign for now. Negative sign is essentially the direction in which the deformation is usually opposite to the direction of the force. Therefore, there is a negative sign. Okay. K into, so we saw here this X, instead of X we can write delta X, which is L minus L by L naught. You can divide it by L naught and multiply it with L naught, and then divide the both terms by A. So this particular term is called stress, and this particular term is called, which is essentially the elongation. This particular term is the elongation, and this is the initial length, is called strain. So strain is essentially, or engineering strain is essentially the fractional increase in length, the change of length by the initial length. And this particular term is known as the Young's modulus. This is an inherent property of the material because the area would change, but the area and length the initial area would still remain the same. This is the initial area. So for all intents and purposes, given that the area, the length, and the spin constant of an object is the same, the Young's modulus remains the same despite the dimensions of the material. It's also known as normalized spin constant. So this particular F is equal to minus K delta X becomes stress is equal to strain, stress is equal to strain into Young's modulus, or Young's modulus can be defined by now the linear relationship is valid for very small strains, less than 1. And this also depends on the type of the material. If the inherently the material is very elastic, they will hold the relationship for long. The other kind of stresses that object might undergo is tensile strength or compressive strength. Again, tensile strength is when the intent is to elongate the material, whereas compressive strength when the force is applied with the intent of decreasing the size of the material. So for tensile strength, sigma is greater than 0. Essentially, the stress is more and the strain is also greater than 0. For compressive strength, stress is less than 0 and the strain is also less than 0. And general units are pascals. Strain, however, is unitless because it's a ratio between two two lengths, L minus L naught by L naught. So apart from, so there are different Young's modulus or elastic modulus is one type of modulus. There are other different stress strain relations. There is bulk modulus, there is shear modulus, there is compressive modulus, etc. Since we saw that the bone can control only a little bit of shear strain, we can look at shear modulus, which is essentially the job base. Essentially, there is a shift in the angle, the shear deformation. This is the deformation. Theta is the deformation with a force F applied along this plane. Therefore, the shear stress is F by A is the cross-sectional area of the object. The shear strain is usually tan theta, but for very small objects, very small deformations, it can be assumed that the shear strain becomes theta. So, if G is the shear modulus and tau is the shear stress, gamma is the shear strain, tau is equal to shear modulus into shear strain. Again, shear modulus is also a property of the material and not dependent on the changes that the material would undergo in ideal scenarios. The shear deformation is also related to the torsion of, if there is a cylinder here and it is turned, the torsion that is generated, the shear deformation controls that, where the torsion T is related to the deformation angle theta. So the movements or the stressors that a bone might encounter can be tension, compression, shear, bending, and torsion. These are the kinds of forces that the bone would encounter and the strains would come out of that. One more, so if an object is under tensile or compressive forces, even though the modulus does not change, there is a change in the shape. The volume of the object might not change, but the dimensions of the object change. The assumption in other stress strain relationship is that the cross sectional area of such a cylinder does not change. However, this is not true, that it does change to a certain extent. And if the fractional strains in the x and y directions are Ex and Ey, we can define a term known as the Poisson's ratio, which is a relationship between the longitudinal and lateral strains provided by the Poisson's ratio, which is provided by the Poisson's ratio. If Ex and Ey are in x and y directions respectively, the Poisson's ratio is Ey by Ex, and there is a negative sign because Ey is in this direction and Ex is in this direction. For isotopic materials, the range possible is -1 to 0.5. However, it's very it's not possible to find materials with negative Poisson's ratio. Uh, these are hypothetical setups wherein the range is in negative. For anisotropic materials, uh, the Poisson's ratio can exceed 0.5. For metals and many engineering materials, which for all analytical purposes are considered to be isotropic and homogeneous, the range is in 0.25 to 0.35, which is uh, more or less uniform, whereas for bone it ranges from 0.21 to 0.62. Again, for soft tissues it is considered to be 0.5. If the Poisson's ratio is uniform, then the Young's modulus and the shear modulus can be uh, linked by this particular formula, given that the material is isotropic. If the material is anisotropic, this relationship fails. Okay, coming to a stress strain curve, uh, the if you are to pull on a spring, the spring will expand up until a certain point, after which there is a degradation in the spring behavior, right? And up until this point, the spring can come back to its original state. However, after this point, the spring enters the plastic regime, where it can no longer come back to the initial point. It might enter into hysteresis, which is when, if a material has entered a plastic regime, it can no longer go back to its initial point. It can not come here anymore. And this kind of a relationship is also seen if you were to plot force and displacement. Okay. For stresses beyond the elastic limit, there is permanent or plastic deformation, and the length and the shape of the object are different from the stresses removed. If it hasn't entered into failure, you will see something known as hysteresis. The yield point wise is at a stress somewhere higher than elastic limit, after which if the elongation is increased, or if the load is increased, the material enters into plastic deformation. Okay, so if you were to observe the stress strain relation in this region, it's a straight line and the slope is the Young's modulus. This is the proportional limit, after which, even though the object is elastic, it becomes non-Hookean. Here it follows the Hooke's law. After the elastic limit, it enters into the plastic regime. There is very little extra stress that is applied to change the strain, and after a point the object fractures, or there is failure of the object, in which it can no longer come back to a initial state. Even if the initial state is here, it essentially fractures, it breaks down. Okay, and the stress strain relations can look very different for different materials. It can look something like this for ceramics, like this for metals, and like this for polymers. And in terms of analysis, ceramics can mimic the relationship for bones under certain approximations. So ceramics have a relatively linear stress relation with a large slope. Just a second. and the fracture point appears little into the non-linear elastic regime. So this portion is very less for ceramics. Bone, for under certain approximation and assumptions, can act like ceramics. Metals have a smaller Young's modulus, large non-elastic and plastic regime, so the breakdown is very fast. Elastomers can have a very small linear regime. And after it, once the molecules are straightened out, there is a very low stress required to change to get a very high strain. Blood vessels are considered to be elastomers for the different analysis. So if we compare the mechanical properties of bone with different common materials, if you were to see cement or concrete, the Young's modulus is 16.5, whereas for steel it's 207 gigapascals, whereas the compact bone, the hard bone, has a Young's modulus of 17.9 gigapascals, whereas the trabecular bone is like one order less than the compact bone. It is 7.6 megapascals. The compressive strength is 21 uh, megapascals for concrete, 552 megapascals for steel, and 170 megapascals for bone. Tensile strength is 2.1 for concrete, 827 for steel, and 120 for compact bone. So for all, we can say that the mechanical properties of bone fall somewhere in between concrete and steel, which is a very essentially a very high uh, tensile strength. Okay. Other biological materials that are present in that: cortical bone, similar to ceramics, tendon and ligament have very low Young's modulus. Uh, Cortical bone has very high Young's modulus, and cartilage and trabecular bone have Young's modulus even lower than tendon and ligament. Essentially, you can compare the slopes in the elastic portion, and you can comment about how much is the Young's modulus. If it's high stress, low strain, Young's modulus is high. If it's low stress, high strain, and everything that is intermediate will fall within these two extremes. And as you can see, the curves are very non-linear for many soft human tissues, and the tissues are also very anisotropic, and therefore it stretches more easily in the transverse direction than the longitudinal direction. You can compare the mechanical properties of various biological materials. The maximum tensile strength that the different materials can tolerate, within that, hair has the highest tensile strength, with uh, different compact bones falling just beyond the hair limit, whereas various arteries, large intestine, esophagus, all of these have very low tensile strength and very low Young's modulus. So elastic properties can be anisotropic, meaning that the properties are different along different directions. If you considered XYZ axis, even if the properties are uniform in the YX plane, it might be different in the Z plane. This is especially true for bone and esophagus, which are composed of very different materials, so each layer is different. if each of the layers that organ has is different, then the material properties are also going to be different. Many of the biological materials that are anisotropic, whereas common materials such as wood, metal, steel, etc. are isotropic. And the elastic properties of these anisotropic biological materials vary with age. With age, there is a decline in the formation of different materials within the body. The maximum there is more degeneration than regeneration with the age, and therefore the properties also change. The density changes. With density, the if we are to consider bone, with the change there is a decrease in density, which increases the porosity, which essentially leads to osteoporosis, which often lead to fracture in different bones if someone was to fall. If therefore also, when old people fall, when aged individuals fall, they, and if they break their bones, the fracture takes more time to heal because the osteoblastic activity is less, decreases with age. If we are to define strength as the largest UTS, then of the all body components, it's not bone, not dentin, but hair, which has the highest tensile strength. Even with, in terms of Young's modulus, hair has more Young's modulus than, say, bones. Although tooth enamel has still more UTS than hair, which is the hardest biological material in the body. Okay. Now coming to some analysis where we understand how bones fracture when they are bent, such as when there are accidents, when they are even in normal activities, bones will bend, but the bending is within the range, within the tolerance range for the bone. If it enters into the fracture region, then into the failure region, then the bones will fracture. So the setup is, if this is the bone, there is a force F that is being applied at the middle of the bone at the equal distances from both the sides, and these two are fixed. So if we were to calculate the moment along this in positive direction is 0. So F, and you assume the reaction force B, reaction force A. Since the moment arms is 0, the moment along for RA is 0. F is at a length of L by 2 and it has a clockwise movement, so minus sign. RB has a movement in this direction, so a positive sign. RB has a positive sign, and the length at which it is acting is L. So it is 0. So RB is F by 2. And you apply Fy, you get that RA is also F by 2. So the forces are equally divided in both the ends, the reaction forces. Now, if the fracture happens, if there is a slice somewhere here at a distance of x, and we just look at this area, remember in equilibrium, delta fx, sigma fx, sigma fy and sigma m, all of these are 0 if they are in equilibrium. If the system is dynamic, these equations no longer hold true. Okay. Say there is a split here at some distance x. There is some internal force V that is uh, happening here. So if we consider my Fy is equal to 0, this is as the positive direction. F by 2, since we are just considering this slice, we are ignoring this F. Okay, F by 2, which is in positive direction because it's a reaction force to this F, minus V is equal to 0. So V becomes F by 2. So this V is essentially the shear force that is there present internally in the material. So there is apparently only one force acting on this piece of beam with a upward force of F by 2 in the right support. Okay. Now we know that the internal force is F by 2. So V is equal to F by 2. And we know there is some torque because of this F by 2. So the internal forces, which is in the opposite direction, essentially is balancing the external force. Sorry. And this force is called as the internal shear force. Now the torque that if this is the axis along which the moment is calculated, there is an internal torque being applied, which is x F by 2, because the distance is x in the negative direction, is called the internal bending moment, or just essentially the bending moment. For sorry, if you were to see the distribution of shear and moment along the shear and moment in the along the bone, you can see that the shear is positive in this direction, negative in this direction with the length, and the moment is highest here. It decays on both the sides. Coming to the angle of the bending, if the bone is bent like this, this length is less than L and this length will be more than L. There will be some axis which has a length L, and this is known as the neutral axis, where the fibers are unstressed. In this region the fibers are compressed, and in this region the fibers are elongated. If the bend angle is alpha, somewhere along here, and if the radius is r for the neutral axis, um, for very small alpha, L is equal to r alpha. It's basic trigonometry. If alpha is very, very small. So alpha can be written as L by R. Now, if you look at the length as a function of y, where y is this is essentially L minus R minus y into alpha, because the angle is still the same. So the original length is R alpha, and at any length y, the length is R minus y into alpha. So if you look at the deformation, which is Ly minus L naught, so Ly is R minus y. This is the deformation. R minus y into alpha, which is L by R, minus L. R L L minus y L by r minus L. L will get cancelled. So the deformation is minus y L by r. Or minus y by r into L. Okay. So the strain is essentially minus y by r, and depending upon what is the depth of what is the position of y, the strain will change. If the elongation is minus this much, the strain would become this much. Okay. The top portion is compressed, has a length less than L. The bottom portion is greater than L. And somewhere in the middle there is no compression. This is the neutral line again. One more thing is that, as we saw, there was a lot of internal forces that is acting, which was F by 2. Now there is also internal torque, because these forces will also generate internal torque, and this torque will be in this direction because the force is compressive here, and will be in this direction because the force is elongating here, and so the resultant torque will be in this direction. So what these all internal torques can be summed up as tau internal, and whatever torque is felt is the sum of tau internal with half of Fx. Which is essentially 0 because the moments are the forces are 0. So tau internal is essentially minus half of Fx. Okay. Now if one more, we'll add one more axis. There is also a change in the area of the bone. If consider a beam with an arbitrary but constant cross section, the distance up to the neutral axis is y, and the cross section element is a area dA at this position. So dA can be written as a function of y into dy, whereas wy is the width of y, which is dependent on the term y. Whatever forces are acting on this area element is going to be sigma y dA by y, dA of y, and if we were to sum all of these up, if the torque would be minus y dF, and you basically essentially multiply minus y in both of the sides of this equation, and if you integrate it, the integration will give you the total internal torque, tau internal. In this case it will be some d by 2 minus d by 2. Does not depend on the on y, so x is an independent term. There is no the integration does not hold for this. The total becomes minus half of Fx for the tau internal. So if you had to equate this, you will get, you can substitute sigma y by this term. Now y is the Young's modulus and r is the radius of the bending, both of which are constant. So these two can be taken out of the integral, and essentially you are left behind with this. For a symmetrical situation, you can assume y to be d by 2 and yb to be minus d by 2, say. So this particular term, which is under the integral, can be defined as the area moment of inertia. This is different from the mass moment of inertia. It essentially sums up the squares of the distance from the plane, while the other sums the squares of the distance from an axis. So this is a square. This is from a plane, whereas the other one is from an axis. So essentially the bending moment, which is the tau internal, is minus y by r times the area moment of inertia. And you can also IA by r is equal to mb by y. So if IA is larger, in case IA is larger, the mass is distributed far from the central action, which is what we see in a bone. There is less bending for a given bending moment. As you can see from this equation. If the mass from the neutral axis, basically the mass from the neutral axis provides the resistance for bending. So if IA is larger, MB will be small. These I beams are also follow the same principle as the bones, where instead of solid beams, there is a same overall cross section area. The cross section area would be the same, but it is in a I shape. So there is a lot of the beams can handle a lot of tensile strength. However, strain. However, they weigh less. So less expensive and less manpower spent. And due to similar reasons, the long bones that are usually present in the body are hollow, so that they have sufficient resistance to bending, and the per unit mass the bending is the resistance to bending is lesser. If it were a solid bone, per unit mass the resistance will be less. Given that it's not a solid bone, there is a hollow inside, the weight is less, the resistance to bending per unit mass is also larger. Okay, I will discuss some questions pertaining to I hope you can see the screen. Okay, coming to the first question. The hardness of the bone is due to collagen, tropocollagen, hydroxyapatite, and elastin. The answer is hydroxyapatite, which are calcium and phosphorus crystals that are deposited on top of the bone. Which of the following types of bone cells are responsible for resorption of bone during bone remodel? Osteoblasts, osteoclasts, osteocytes, and chondrocytes. Now, osteoblasts are responsible for depositing various material. Remember, blast is responsible for deposition, clast is responsible for breakdown. Sites are usually just present there and perform other homeostatic functions than formation and degradation. So any word with blast is usually responsible for formation or generation of something. So the answer is osteoclasts. Now there is one more thing, chondrocytes, which are responsible for cartilage development. Cartilage, they're essentially present in the cartilaginous components of the body. Answer is osteoclasts. What What is the central canal within an osteon cord? Remember, the osteon is a basic unit that you would find in a compact bone. And the answer is Hawaiian canal. Which of the following statements is true? Bone tissue is homogeneous along its length. Bone tissue is neither homogeneous nor isotropic. Physical properties of bone have been accurately measured. Trabecular bone is denser than compact bone. The answer is bone tissue is neither homogeneous nor isotropic. The physical properties of bone, although widely studied, have not been accurately measured because they fall under a distribution. There is no constant value to it, and compact bone is denser than trabecular bone, not the other way around. Which of the following cross-sectional shapes of a beam will provide great resistance to bending? Rectangular, circular, triangular, and T-shape. We just looked at it. The answer is I-shaped, not T-shaped, I-shaped. Which of the following statements best describes Wolff's law? Bone is deposited and reabsorbed to achieve optimum balance between strength and weight. Trabeculae in the cancellous bone tend to line up with the directions of principal stresses that they experience. Both phenomena occur through self-regulating mechanisms that respond to mechanical forces acting upon bone tissues. All of the above. All of these are true, so and the answer is all of the above. Which of the property allows a material to undergo reversible deformation even when it deviates from Hookean behavior? Brittleness, elasticity, ductility, plasticity. Brittleness is how brittle a material is. That is nothing to do with reversible deformation. Elasticity is the answer. It allows the material to undergo reversible deformation. Ductility is when you are stretching a material, and if it's ductile, the length changes. Plasticity is ductility is usually a property of metals. Ductility. Plasticity is refers to the non-reversible deformation and it's also a non-Hookean behavior. What is the term for the applied force per unit area in the context of material deformation? Elongation, strain, stress, spring constant. The answer is stress. Stress is F by A. Elongation is just the change in the length. Strain is elongation by the initial length. And spring constant is something that is specific to the material itself. Poisson's ratio is a measure of the ability of a material to resist deformation under stress, the ability of material to store energy under stress, the ratio of lateral and axial strains when a material is stretched or compressed, the ratio of lateral and axial forces when a material is stretched or compressed. The answer is the ratio of lateral and axial strains when the material is stretched or compressed. The formula was minus change in the elongation in y-axis by the elongation in x-axis. The normalized spring constant in the equation sigma is equal to epsilon y is Young's modulus, stress, strain, elongation. The answer is Young's modulus. This is the stress term and this is the strain term. Okay. Are there any questions or any doubts? Please let me know if you have any doubts. If there are no doubts, then thank you for listening. I'll end the call.